Come back to Maths Made Easy. Today we'll be looking at the DBE 2024 question 2, which is the sequence and series, and also question 3. So now let's dive into question 2. Now question 2.1 says the first term of an arithmetic series is 7, the common difference of the series is 5, and the series contains 20 terms. Now, to make our equation simple for us, let us first start by writing down the details. Let us gather our data. They say the first term. This means that A is 7. The common difference, D, is 5. And the number of terms, the series contains 20 terms, meaning that N is 20. This is where we start. Then we can now answer question 2.1.1. Question 2.1.1 says calculate sum of the series. Now when you talk about the sum, we talk of this Sn, and due to the fact that they told us that this is arithmetic, we know that the sum of arithmetic is given by Sn is equal to n over 2 into 2a plus n minus 1 into d. Now our job from here it is to plug in the value of a, the value of n, and the value of d. So now let us plug in. It means that we are going to have S20 is equivalent to 20 over 2 open bracket 2, our a is 7, plus n, which is 20, minus 1 into d, the difference is 5. Now your job will be to plug this into the calculator, and you get 1090. So this is the answer for 2.1.1. Now we move on to question 2.1.2. They say the original arithmetic series is extended to 75 terms. The sum of these 75 terms is 14,400. Using sigma notation, write down an equation for the sum of the added to the original series. Let me read the question once again. The original arithmetic series is extended to 75 terms. The sum of these 75 terms is 14,400. Using sigma notation, write down an equation for the sum of the terms added to the original series. So now they say sum of this first 75 terms is equals to 14,400, and initially we had sum of the first 20 terms was equivalent to 1090. So this means that the extended will be the S75 minus the original series, which is going to be 14,400 minus 1090, and then mathematically sum of this number of terms, if you write it using sigma notation, we know that sigma notation is going to be, this is our sigma notation, starting from 1 ending at 75, and we are going to need here the general term. So what's going to come in here is the general term. Also, sum of the first 20 terms, it's n1, so that is 1, it ends at 20, and what comes in here is the general term. And then on the other side is going to be 14,400 minus 1090, which is 13,310. So now what is left of us to do, it is to calculate the general term. So we all know that this is arithmetic, and knowing that it is arithmetic, we know that the general term of an arithmetic sequence, it is given by Tn is equals to A plus n minus 1 into D, where our A is 7 and our D is 5. So our job is to simplify this. So this is going to be 7 plus 5n minus 5. This gives us 5n plus 2. So we plug in that into our sigma notation. Is 5n plus 2, 5n plus 2, and then we continue with our equation. The law of sigma notation says that we can subtract the two sigma. So this is how we subtract the two sigma notations. So the general term is the same, so I write it down. We still have 13,310. It initially started from 1, it ended at 75, and then we subtracted the one that started from 1 and ended at 20, meaning that if we subtract the one that started from 1 and ended at 20, it means that we need to continue from 20, meaning that a number that follows 20 is 21, and then we are still ending at 75. So this is our answer for 2.1.2. Moving on to 2.2, they say that the sequence of the first differences of a quadratic number pattern is 1, 3, 5, ... meaning that it continues that way. 2.2.1 says if T99 of this quadratic pattern is 9,632, calculate the value of T98. So now before you can answer this, you need to have a picture of what they are talking about. So now let us do a rough sketch here of what they are talking about. So for the quadratic pattern, we don't know T1, we don't know T2, we don't know T3. It continues that way, but there is something that we know. We know that the sequence of the first difference, which is this one, it's gonna be 1, 3, 5, and then it continues that way. It continues that way up until it continues, but our focus, it is to get up to T99. So we are going to have T98 somewhere here, and then T99, which is 9,632. So this is what we have here. So we know that a quadratic number pattern has got a constant second term. So how do we get T98? To get T98, we must find the difference here. We must find out what this difference is right there. And how do we calculate it? We find the general term of the first differences, and the general term of the first difference is given by A plus n minus 1 into D. A is 1, D is 2. We simplify it. This is going to be 1 plus 2n minus 2, and our general term here is going to be 2n minus 1. So this is just the general term. So to get the differences here at T98, I'm going to sub in 98 in here into this equation. When I put in 98 into this equation, let me use a different color pen. T98, it gives me 2 into 98 minus 1, and that is, when I put it into my calculator, it is 195. So meaning that the number that comes here is 195. 95. So to get T98, I know that this one minus this one will definitely give me T98. So I get into the calculator, I say T98 is equivalent to 9,632 minus 195, and my answer right there is 9,437. Now question 2.2 says if it is further given that the third term of the quadratic pattern is 32, determine the general term of this pattern. In other words, determine Tn of this quadratic pattern. So as we have already done, let's expand it once more. So it's 2.2.2. We don't know what T1 is, we don't know what T2 is, but they tell us now that T3 is 32, and initially they had told us that this is 1, another one is 3, another one is 5, and so forth. So we had found that the second difference is 2. So the question says determine the general term. So how do we find the general term? This is how we find the general term. You know that 2a will always be equivalent to the first difference. The second difference. 3a plus b will always be equivalent to the first term of the first difference. And lastly, a plus b plus c will always be equals to the first term. So now let us try to solve our equation. 2a is equivalent to 2. We solve for a, and our a is 1. 3a plus b is equivalent to 1. We solve for a. We are going to have 3 into 1 plus b is equal to 1. This is 3 plus b is equals to 1, meaning that the value of our b is equals to 1 minus 3, which is negative 2. Now we need to find the value of c. So we have a, we have b, we have two unknowns in this case, so it won't really work. So this one won't really work. So the alternative that I suggest that at this point we know that Tn is equals to an squared plus bn plus c. We don't know what c is, but there are things that we already know. We know that Tn is equals to n squared minus 2n plus c, and they also told us that T3 is equals to 32. So I put in 32 here, and then where there was n, I put in 3. And then when I get here, I solve for c. So this is going to be 9 minus 6 plus c. 9 minus 6 is 3. Continue. 32 minus 3 is 29, meaning that Tn is equals to n squared minus 2n plus 29. That's how it goes. Moving on to question 3. The question 3 says a circle with radius 6. So the circle that we're currently having here, the radius from here to here is 6, is drawn, and the second circle, which is this one right here, smaller circle, is drawn through the center of the first circle, and it touches the first circle internally. As we see, it touches it internally as shown in the diagram. A third circle is drawn. Here's the third circle through the center of the second circle, and it touches the circle internally as well. We see it right here. The process of drawing the circles continues. So I think there is something that we notice with these circles. The radius of the first circle, which is the bigger one, is 6. The radius of the second one is going to be how much? So the radius of the second circle is going to be half this one. And then the radius of the third circle, we know that this third circle is going to touch internally as well, and is going to start at the center of this circle right here. So we know that the radius of that circle is going to be half 3.1 is going to be half the radius of that one. The first radius is 6, the second one is half 6, the third one is half 3. So we keep on multiplying by half. So the radius of the third one is going to be 1,5 centimeters. So now we move on to 3.2. Calculate sum of the areas of the first 10 circles. So in other words, they want sum of the areas of the first 10 circles. So now let us write down the area of the first circle. We know that the area of the first circle is going to be pi r squared. So we are going to have pi, our r is 6 for the first circle, squared. So this is going to be 36 pi. The area of the second circle is pi r squared as well, and then our r is 3 squared, meaning that the area is 9 pi. The third circle, it's pi r squared as well. The area is 3 over 2, meaning that we have 9 over 4 pi. I'm sure by now you can recognize the pattern that we are having here. So this is our T1, T2, T3. So let me write it down so that it can be clear. T1, T2, T3. It continues. The question says calculate sum of the areas of the first 10 circles. So you can tell that our A is 36 pi. Our R is T2 over T1, which is 9 pi over 36 pi. The pi cancels each other out. We have 1 over 4. And then N, the number of terms. We are talking about sum of the first 10 circles. So now that we have gathered all this data, we can calculate sum of the first 10 circles. So sum of geometric sequences is given by Sn is equals to A into r to the power of n minus 1, all divided by r minus 1. We are summing 10 circles, so we could place n by 10. A is 36 pi, r is 1 over 4, n is 10 once again, r is 1 over 4 minus 1, and then we sub this, or we put this into the calculator, and we get the answer. The answer is 150,80. Our answer is 150,80. We move on to question 3.3.3. I'm gonna try and squeeze it in here. Question 3.3, they say which circle has a diameter of 3 over 128 centimeters. So now as soon as you get to this point, you take a chill You think about it. You don't want to get yourself confused. They say which circle has a diameter of 3 over 128. But you look back to what we've been doing here. So what we've been doing so far involves no diameter. We've been talking strictly about, let me show you. Yeah, what we've been doing so far, we've been talking strictly about the radii. So this diameter that is given to us, we are going to write it in terms of the radius. We know that radius is always half the diameter. So our radius will be half times the diameter. So it's 3 over 128. We put that into the calculator and we get it to be 3 over 256. So we check which circle has a diameter of 3 over 128, which subsequently mean which circle has a radius of 3 over 256. So how do we get to that? We know that our circles, the radius of our circles, the bigger circle had a radius of 3, the second circle had the radius of the bigger circle had a radius of 6, the second circle had a radius of 3, the third circle had a radius of 3 over 2. The pattern continues in that particular format. So now looking into that, this is geometric. The value of A is 6. The value of R is T2 over T1. In this case, is 3 divided by 6, meaning that the ratio is R. And our general term for the radii is A times R to the power of n minus 1. A is 6. R is 1 over 2 to the power of n minus 1. This is our general term. So to get which circle has a radius of 3 of 256, we equate 3 over 256 to the general term. And then from here we solve for n. Now how do you get to solve for n? I divide this side by 6 and also this side by 6. 6 cancels each other out. What is left on the right is 1 over 2 to the power of n minus 1, and what is left on the left is 1 over 512. So but you look at your equation here, whatever that you're trying to solve here is at the exponent, and we know that the laws of exponent always say that when solving for the exponent, when bases are the same all the times, meaning that what you need to do here, we need to write this number in terms of base 2. So can we do that? Yes. 512 can be written as 2 to the power of something. So 512, if you don't know how to do that, if you're using a Casio, you go to the Casio calculator, you insert 512. After putting in 512 into the calculator, you say equal sign, shift, fact, it will give you 9, meaning that 512 can also be written as 1 over 2 to the power of 9. So now the bases are the same. So when the bases are the same with an equal sign in between, I can equate the exponents. Therefore, the circle that will have the radius of 3 over 128 is circle number 10. Thank you so much for watching the video. See you in the next video.